All right, welcome back again. Now we're going to go through Chapter 18. Chapter 18 discusses actually two topics, and these are actually separate topics. Chapter 18 deals with chemical equilibrium, but before that it talks about chemical kinetics. So what we should say is Chapter 18, chemical kinetics, and chemical equilibrium. Kinetics is how fast the reaction proceeds, and equilibrium is where the reaction ends up. And so let me add that in there. Speed of the reaction, and equilibrium is where the reaction ends up. That is, once the reaction has gone to completion. What do we have? Do we have just products? Or maybe there's leftover reactant? Or maybe it's all reactants left over. And so that's equilibrium is where we end up once things stop progressing. And so we're going to be looking at these two topics separately and then seeing how they're related. And so we'll skip the learning objectives here and then okay, actually we're going to look at equilibrium here first, but maybe we should look at kinetics. Let's take a look at kinetics first. All right. So kinetics, we're looking at collision theory, kinetics. In order for a reaction to occur, we have to have a collision. And so these collisions are collisions between the particles, molecules, atoms, whatnot. We have to have enough energy. So there are two things. Sufficient kinetic energy is one thing that's required in the collision, and proper orientation. So this is for a successful collision. And so let's look at if we have, these are the two things here. One, enough kinetic energy and the proper orientation, and then we'll have reaction occur. And so these are the ingredients that we need for the collision to be successful in order to get reaction. All right, taking a look at that, here is a successful collision. One, the orientation of the blue molecule and the red molecule is correct, and then they have enough energy. Enough energy to do what? Enough energy to break the bonds here and form new bonds. And so breaking the blue-blue bond and making the blue-red bond here. And that's what we end up with. Here's a collision with incorrect orientation. Well, actually, orientation is not bad, but not enough energy here. And so what happens is these two molecules just bounce off each other. And the same thing here, the orientation is not good. Maybe the energy is okay. They bounce off. And so out of all the collisions, there's lots of collisions occurring. These are lots of random collisions. But out of these lots of random collisions, there's a small subset that are like this. This is a low percentage of those collisions, most of the collisions, are like this. This is kind of a higher percentage of collisions. And it depends on how complex the shape is. And so this would be a higher percentage, these unsuccessful collisions. And for orientation, this is just randomly oriented, but for energy, what we have is we also have a distribution of energies, the Maxwell-Boltzmann distribution. And what we have here is an energy required, E sub A. And so that's the energy that's required in the collision. E sub A is called the activation energy. And the activation energy has to be enough energy to break the bonds. But it's not just the bond energy. It's not how much energy it takes to break this bond, because we also form this, which we call an activated complex, or what we call a transition state. This is a transition state. And so we're transitioning from the reactants over here, to the products over here. And the transition state is going to require a certain amount of energy to generate transition state, and that certain amount of energy is called the activation energy. That's the energy required to form this. And so, out of all the molecules here, there's going to be a small population of molecules with enough energy to do that, just that. However, even here, there's going to be an even smaller subset of molecules with the correct orientation. So, how many of these have the right orientation to react? And so, it's even smaller subset of those. The bulk of the molecules will not have enough energy, and the bulk of the molecules will be down here, let's say. Um, of course, if we increase the temperature, that'll shift this to the right. If we shift this to the right, then the proportion is going to grow. And if the activation energy, is there other things? Activation energy might be weaker, so some reactions occur very fast because they don't require much energy, and most of the population might have enough energy to break. So let's say the activation energy will way down here, then the reaction should happen very fast because a large population will have sufficient energy. When we shift the activation energy further to higher energies, practically nothing happens there because there's so few molecules that can react. And so temperature is going to influence the speed of the reaction, because the temperature will shift the population to higher energies or lower energies. And the activation energy will, because the activation energy depends on the reaction. It depends on how strong the bonds are, etc. Reaction. And so that can also influence how fast a particular reactions occur. So this is kinetics. Energy changes during molecular collision. So what we do is we kind of monitor this. The energy change is we have delta E. It could be an exothermic or an endothermic reaction, and we call this the progress of the reaction. If we monitor the reaction progress, we start off with reactants here. And the reactants are going to have a certain energy associated with that. And the energy is going to be given on the y-axis, and this is just kind of arbitrary units here. And what has to happen is there has to be a collision with enough energy to make the transition state. And so this is the activation energy here, and then we have a transition state here. The transition state is not actually isolated. It's just a transitory state in which bonds are breaking and bonds are forming. And so that's going to be at the peak here. And then it'll either go here to products, this would be an endothermic reaction, because overall, the energy between delta E, that is the energy between the reactant and the product, is positive here. Delta E, this would be endothermic. It could be potentially exothermic, so let's say it drops down here instead. And so this could be A, an endothermic type reaction, or B, an exothermic type reaction. An exothermic reaction, the products are going to be at a lower energy down here, so this is delta E. We'll look at the product here. And so we can chart the progress of the particular reaction. It might be endo or exo, or it might be the same energy, if it drops down to about the same energy here. And so this is the progress of the reaction. I think activation energy. Well, this is all. This potential energy barrier, ignore that. Just think in terms of activation energy is what we need. Activation energy is the minimum energy, kinetic energy needed to produce an effective collision, but we also have to have orientation as well. Okay, this is the progress of the reaction. When I look at this reaction, this is overall exothermic, because over here I have my reactants, over here I have my products. And so going from reactant to product is going down in energy. So this is exothermic, delta E. But in order to get there, we have to have this collision. The collision's endo, but the reaction overall is exo, because, we climb up this hill, but not only do we go down the same amount, we go down even further. So net, We go up this amount of energy, down that amount of energy, and then down more. And so overall reaction is exothermic. In order to go forward, we have to overcome this barrier, this hill. Depending on how big this hill is, that's going to dictate the speed because it depends on the population of A2 and B2. You know, how many of these, let's say these are the bicyclists, how many of that population can make it over the hill? In this particular instance, going backwards is even tougher. Look at the activation barrier. And so if we want to go backwards, we have to climb this hill, which is much higher in that sense. Well, anyway, here's a successful collision. Successful collision's got to have two things. One, orientation's got to be right, and so this looks properly oriented. And two, it has to have sufficient kinetic energy to make it to the top of the hill, and then it can drop down the other side. So in this particular case, we make the transition state. In this transition state, the bonds are breaking here, and new bonds are forming. And so it's a transitory state, and it's not actually isolated. And then we have the products here at the end. So this is their reaction progress, or sometimes called a reaction coordinate diagram, the coordinates of the reaction. This is just showing the activation hump, going over. This one has more than enough kinetic energy to make it over the hump, but this one doesn't. Kind of rolls, almost gets to the top, and then rolls back. And so this is not energetic enough. In this activation hump is what we call potential energy barrier, I suppose, but not really. It's the amount of energy that's required to make the transition state up here. And so, in a sense, not enough molecules might have it, or maybe lots do. Well, you're going to have that much energy to make it over there. All right, when we look at the rate of the reaction, the conditions that affect the rate of the chemical reaction, of course, the temperature is, because that's going to shift the population, and the activation energy. Those two things can have an impact on the speed of the reaction. And so here we can see the temperature effect here. The blue is 25 degrees, the red is 75. So 75, the whole population is shifted right. The activation energy, they haven't changed. It's just fixed here. So at higher temperature, you're going to have a greater population. This is a Maxwell-Boltzmann population distribution for the energy. Okay, there are certain things we can do. So, for example, the activation energy is kind of fixed for the reaction. Some reactions have high activation energy, some have low activation energies. But that's kind of something that's fixed. Now, there are things that can alter where that activation energy lies. So, for example, a catalyst here. What catalysts do is they provide an alternate pathway, an easier path. So rather than having to climb over the mountain, they can go around the side of the mountain, let's say. And that lowers the activation energy. If it lowers the activation energy with a catalyst, it's a catalyzed reaction, then you're going to have a much greater population that has enough energy to react versus uncatalyzed reactions. So catalysts will speed up the reaction by increasing the population that is able to do it, go over the hump. Excuse me. Conditions that affect the rate, affect the concentration. Of course, the other thing is you can just increase the population. If we increase the population all around, that's going to increase the population lower, and that's going to increase the population higher. So higher concentrations will make reactions go faster as well, because you're going to have more collisions. The more collisions you have, the faster the reaction is going to take place regardless. And so that's what they're saying here, the effective concentration here. And so high concentrations, high rate of collisions, which increases the rate of reaction. That's basically. Okay, that's kinetics. And so those are kind of the factors that influence kinetics. Now, the next part we're going to look at is, kinetics deals with how fast the reaction occurs. Equilibrium deals with where the reaction ends up, And so we're going to talk about, I'm going to go back to the first slide here, conditions of equilibrium. In equilibrium, there's no more change. These are usually dynamic equilibria. There's no more net change, but there's always particular level changes. So anyway, when we have an equilibrium situation, the changes are reversible and can be represented by the double arrow. which we talked about earlier. Equilibrium is a closed system, dynamic in nature. Closed system is where, no matter leaks out. It's a dynamic. We have open systems too, where open systems matter can leak out. In a closed system, energy can leak in or leak out. But this you don't have. In Chem 1A, we talk a lot about these, but in Chem 4, not so much. Chem 4, we talk about dynamic equilibrium, so you should know dynamic equilibrium. That's what we did. And this is a case where the changes occur in equal and opposite rates, basically, here. But it results in zero net change, Okay, so here we have reversibility of the chemical reaction here. Let's see. We have calcium and bicarbonate. Bronzite acid base. Oh, no, this is a precipitation reaction. We're going to get calcium carbonate and some CO2 that forms. And then they're showing, which I think they're showing calcium and bicarbonate, adding CO2 to go back. And so adding CO2 to this, they're forcing this reverse reaction and going back to the original state. So this is an example of a reversible reaction in which they can go forward or backwards in both occurs. How on one side may be favored, depends under normal conditions. Okay, so that's the equilibrium, and then this is the kinetics. So we're going to go back to equilibrium up here. Okay, development of a chemical equilibrium. And so for any reversible reaction in a closed system with opposing reactions occurring at different rates, the faster reaction will decrease and become slow. The slower reaction will increase and become faster. Don't worry about this. Opposite rates will eventually become equal and equilibrium will be established. And this is kind of intuitively seen here. If both reactions, initially we're just going to have forward because of no product. As the product grows, then we're going to have reverse reaction. And eventually we'll hit a state of dynamic equilibrium. This is the state. From here on, it's dynamic equilibrium, where the forward and the reverse rates are equal and there's no net change. Here there is net change because we're net forming product. And the more product we form, the more reverse reaction we get. And so this is what we call approaching chemical equilibrium or dynamic equilibrium. Okay, once we establish an equilibrium, let's say we have an equilibrium that's established. And so let's say this is favored, reactants favored, and so we got, product forming and product decomposing, some kind of equilibrium like this. There's ways to do this. Once we establish an equilibrium, then what we can have is we can have a shift in the equilibrium. And so what we do is we establish an equilibrium and then we perturb it. And that is, we upset that equilibrium so it's no longer at equilibrium. And then a new equilibrium gets established, new equilibrium established. This is Le Chatelier's principle. Le Chatelier's principle says if an equilibrium system is subjected to change, process tend to partially counteract the initial change in the equilibrium system is subjected to change, brings the system to a new position of equilibrium. In other words, that we upset the equilibrium and then it reestablishes. And what they're saying here is that the changes are kind of opposite of the perturbation. And so the concentration effect, let's say we have an equilibrium like this. A plus B is an equilibrium with G plus H. If we increase the concentration, it shifts the opposite way. So for example, if we increase the concentration of A, then it screws up the equilibrium. And then what we expect is we expect a shift to the right. The equilibrium will shift right. In other words, what happens is if we increase the concentration of A here, then the countering effect is the reaction shifts to the forward direction, consuming A in the process, and then we reestablish an equilibrium. Restore, or not restore. I don't say restore because it's not the exact same equilibrium. There's going to be more of everything in this. And so I'll just say reestablish an equilibrium. Let's give a more specific example for Le Chatelet's principle. Le Chatelet's principle is something that you do. So, for example, here we have an equilibrium. This equilibrium consists of 1, 2, 3, 4, 5 yellows and 2 blues. What happens if you add more yellows? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You add more yellows, then what happens is there's going to be a shift. And some of the yellows will disappear and be replaced by the blues. And then we establish a new equilibrium here. So there's a perturbation to the equilibrium. So in this example, we predict the direction forward and reverse of a Le Chatelet shift in the equilibrium. So let's say we establish an equilibrium here with methane, hydrogen sulfide yields hydrogen and carbon disulfide caused by each of the following. Increase the H2S concentration. If we increase the H2S concentration, it should shift right. Because if we increase the H2S concentration, we need to shift right to decrease it, to counter that effect, and to establish a new equilibrium. Increase the hydrogen, that's reactant. Oh, no, that's not a reactant, that's product here. If that's product, then it should shift left. And so we expect a left shift because we need to counter that. And so we're going to have too much hydrogen. The way to counter that is to have the reverse reaction take place and decrease the amount of hydrogen. So those are some examples. There's also a volume effect too. If we increase the volume, it favors the side with more moles of gas. Favors side with more gas. If we decrease the volume, it favors the side with less gas. So let's take a look at an example here, Le Chatelet's principle. So we have two, looks like NO2s and one N2O. And so on the left, we have 2 moles of gas. On the right, we have 1 mole of gas. And so if we decrease the volume, we're going to favor the side with more moles, or fewer moles of gas, sorry. And so we'll prefer N2O4. So we're going to get more N2O4. This is 1, 2, 3, 4. Than NO2. Here we had twice as much. So if we had 4 NO2O4s, we'd expect 8 NO2s. How many do we have? 1, 2, 3, 4, 5. We only have 5. And so what happened was a shift occurred to favor the side with fewer moles. And so when we decrease the volume here, this one shifted to the right. And so we see a right shift. And so we're going to consume some of the NO2 to make N2O4, and we end up with fewer moles of gas, which is better when the volume is smaller. Otherwise the pressure gets quite high. Increasing volume favors the side with more moles of gas. And so that's another Le Chatelet. So concentration, volume, what else? Okay, let's take a look at this. If we reduce the volume, okay, so let's count it. This is gas, that's gas. So there's 3 moles of gas. 1 plus 2, 3 moles of gas. Over here, this is solid, so ignore that. This is 4 moles of gas. So if we reduce the volume, it's going to favor the side with 3 moles of gas, and so we expect to shift left. So left shift, or the reverse reaction. So shift is reverse direction. Okay, the temperature effect, this changes the balance. This changes, the ratio of product to reactant. And so increasing temperature favors the endothermic direction. So one way is endothermic, the other is exothermic, and so we have to figure out which side, which direction is it. And that's a question mark here. Decreasing temperature favors the exothermic direction. And so let's take a look at something here. For example, here. This is exothermic. Exo because heat is a product, and therefore it's exothermic. So increasing temperature favors the endothermic direction. Endothermic is going to be the reverse. You can see heat is going to be consumed. So increasing temperature favors the endo, means more NO2. Decreasing favors the exo, which means more N2O4. And so you can see that here. The NO2 is brown. And so at lower temperature, we favor the N2O4. At higher temperature, we favor the NO2, which becomes more brown. Do you see? There's still brown here because there's some in the equilibrium. So this is kind of balanced situation. This is endothermic in the 4 direction. So it's like this. And so there's a population of N2O4s, some population of NO2s or whatever. N2O4 is the product. So some population of N2O4, some population of NO2. And that's going to change that population here, according to Le Chatelier's principle. So Le Chatelier's principle is important. This is an endothermic reaction. So increasing temperature is going to favor the shift forward. And so let's see. Predict the direction of the equilibrium shift if the temperature is reduced. Reduced temperature. Reduced temperature is going to favor the reverse, because that's the exothermic. If we go backwards here, heat is product. If we go forwards here, heat is reactant. And so expect it to shift. Now, the ratio of product to reactant is actually a constant. It's a little bit more complicated than that, but it's the product concentration. And so this is kind of roughly products over reactants. Reactants is supposed to be here. Officially, K is given by G, let's say just some generic product raised to little GHH. These are concentrations here. What's the light went off? Go turn on the light again. And the equilibrium constant is this. We're going to have A, B, B. Actually, I shouldn't say. We should say probably not G. I need to do different. An equilibrium constant, we're not going to worry too much about that, but this is a constant, and it gets a little tricky because this is for the reaction AA plus BB. This is kind of a generic reaction. This is going to go to GG plus HH. Now, the interesting thing is that this G, we can't necessarily call it G, this A, this B, and this H, and so we call it M, N, we'll just call this OP. Where M and N and O and P we have to figure out. Oops, did we figure that out? No. Sorry. I'm getting the kinetics and thermodynamics. I need to keep the kinetics and thermodynamics separate. Sometimes you'll see A, B, M, N, but this is little a, this is little b, this is little g, this is little h. And this ratio of products over reactants is called the equilibrium constant. And let's see. So, for example, here, when we look at this reaction, where the reaction ends up, the ratio of product to reactants is always the same. Yeah. This is a constant. And so we can predict where the reaction ends up at equilibrium. Reaction ends up at equilibrium at K, the ratio of product over reactant. And the K here is given 51.5. This allows the prediction of stoichiometry. Of partial reactions to be calculated. The stoichiometry we've done so far is just for when we expect 100% reaction, but some reactions don't go 100%, like weak acids, weak bases, that type of stuff. And this is the equilibrium constant here that I had written up earlier, and this is equal to constant. And that's where we get, eventually we need some kind of ratio of product over reactant here. And the product over to reactant ratio is going to come out as K. So once we hit this, then K has been established. K is going to be the HI concentration squared divided by the H2 concentration to the first divided by the I2 concentration to the first. And this is where the reaction ends up at equilibrium from here on out. No, there's no net change. And so one of the active exercises is writing the equilibrium constant expression, which we can do here. We'll move that over here. And so it'd be product raised to the second power here, ammonia squared, divided by the nitrogen here, divided by the hydrogen cubed. And this is going to equal a constant. And so we can determine what that constant is when it's given. Here's another example of equilibrium constant product reactants. So HCl squared is gas, divided by the hydrogen, divided by the chlorine. Equilibrium calculations we're not going to do in this. This is going to be beyond the scope of this class. But this is in Chem 1B. We focus a lot on this. And so for us, we're not. These are all interesting calculations for sure. I'd like to do them, but like traditionally wait until Chem 1B. Otherwise, it's too much stuff for Chem 4. And so this one, oops, I missed one here. A lot of these aren't too bad. This one, this acid constant is very interesting because this acid tells us the ratio of how much is hydrolyzed or ionized. And so the higher the K, the more acidic it is. And so the greater the Ka, the stronger the acid, because the more H plus we get in there. And so this one would be pretty interesting to do, but again, we're not going to do an actual calculation. I'm just going to leave it at that. And so the remaining slides is the same thing. So, oops. This actually goes into quite a lot of depth. So those would skip. Okay, that concludes chapter 18. This is a good review if you're going to Chem 1B to look at it. I mean, we can do one calculation. We can look at one calculation, but you don't have to worry about this being on the test. Let's look at the acid ionization, just equilibrium, just briefly here. So let me Let's do that. So, in other words, the higher the K, the more product we have. The more product we have, the greater H plus. And the greater the H plus, the more acidic we say it is. All right, so a 0.13 molar solution of an unknown acid has a pH of 3.12. This is the equilibrium H plus concentration. So the equilibrium H plus concentration is going to equal 10 to the minus pH molar. This is going to be 10 to the minus 3.2 molar. And then we can punch this in our calculator, and we get an H plus concentration of 7.6 times 10 to the minus 4 molar. And then we can go back through and, et cetera, figure out the percent ionization. Percent ionization in this one is 0.58% after we solve for the original molarity of the acid. You can do calculations of that sort, but again, just ignore it. So that's why I'm not going to go into it in depth. Anyway, okay, that's it for chapter 18. Chapter 19 is next.